more repetition from yesterday. So we discussed two types of databases, the SQL or relational databases and the NoSQL or NoSQL databases. And the basic difference between them is that the relational databases are intended to be used with structured data, and the NoSQL data are suitable for unstructured data. And there are these four types of NoSQL databases: value stores, document-oriented, column-oriented, or multi-column, or column family databases, and graph-oriented NoSQL databases. And you remember this graph, so here we have a comparison of the size of data which can be handled by a database as compared to the query depth of the according database type. These are database types, of course. And as you can see here, the value size, the value databases are the ones which can handle by far the largest amounts of data, followed by the column family databases, and then the document-oriented NoSQL databases. Then come the relational databases, so they can handle much less data than most NoSQL databases. And then finally, the web-oriented databases, even though they are NoSQL databases, they have an even deeper depth, true depth than the relational database. And we also have this comparison chart. So we have here some categories where you can see, okay, the problem is that for relational databases, you can use a standardized tool language such as SQL, while in NoSQL world it's dependent on dynamic schemas. You have no schemas, the schemas are inferred automatically, and SQL scales vertically, NoSQL scales horizontally, and the basic data structures are tabled in the SQL world, while in the NoSQL world there are documents like JSON documents, value pairs, like columns, or graphs. And of course, for the relational world, we require joins. If we have a normalized database, and in the NoSQL world, we have this paradigm that data which are queued together should be stored together. So usually you just store everything at once and don't care about normalization. Of course, you need to take care of the application logic later. And then also an important aspect is that often we don't have full ACID support. So relational databases really always support a multi-vector ACID, while NoSQL databases only sometimes support it, only in a limited manner. So you have to be careful with that and look that up what your database actually supports if you require these kind of features. Okay. So to sum it up, NoSQL databases are advantages for unstructured data in big data environments, and the supported operations are rather simple, so you have to do more in the application logic, and it scales horizontally. Okay, so today we will talk about cluster computing and its relation to cloud computing. So it's not the same, so but of course it's related, and very often cloud platforms rely on clusters, which comes quite naturally given the demand you have for parallelism there. But of course you can do cluster computing also on premise, so it doesn't necessarily be in the cloud. Okay, so first something about data exploration. So I already discussed a little bit different levels of measurement of attributes. So there are several scales of measure. I think most of them you should already know. So we have the nominal scale. The nominal scale is only able to compare something for equality. So you know that something is equal or it's not equal, and that's it. Nothing in between. And the example would be zip codes, right? So The towns can have different zip codes, so you can look up if the zip code belongs to a certain town or a different town, but you cannot really compare the zip codes in any other aspect. So the only property you could measure for the nominal scale is the frequency. And the statistical location parameter you can measure here is the so-called mode. So the mode as a statistical term means it's the value that appears most often in the distribution. So it's called the mode. And then of course, if I have just like zip codes, I could count what kind of zip code appears most often, but nothing more. Then we have the ordinal scale, which has equality or inequality, of course, but also the smaller and greater relation. So this means that you cannot only measure the frequency, but also the order. Because if we know that something can be smaller or greater, then this implies an order. An example would be grades, like at school, I don't know about Vietnam, in the US, in Britain they have like A to F or something, or A to E. In Germany it's usually 1 to 6, so 1 is the best and 6 is the worst. But still, the grades imply in order. So you can say like 3 is better than 2, or larger than 2, or worse than 2, whatever is how it is defined. In this case, you can also calculate a median, right? So the median is if you just sort the values and then take the middle, as you probably know. So in order to sort the values, we need a larger or greater relation. And then we have the cardinal scale, where we have actually 2 kinds of cardinal scale. We have the interval scale and the ratio scale. And at the interval scale, in addition to smaller and greater relation, we also get plus and minus, so that we can actually calculate distances. An example would be the temperature in degrees Celsius. For example, you can say like 40 degrees is 20 degrees more than 20 degrees, and that's twice the amount of 10 degrees more. So we can express distances in this scale, and then the statistical location parameter, which is added here, is the arithmetic mean. You can, for example, say we have an average temperature, I don't know what you see, maybe 27 degrees. In Germany, I guess it's 8 degrees. So plus, yeah, still pretty cold, right? So you can calculate an arithmetic mean. But the difference to the ratio scale is that for the ratio scale, you can actually express 2 ratios by using multiplication and division. And in this case, you also get a natural 0 point. I mean, what of course comes to your mind here, if you look at the temperature, is the temperature in Kelvin. So the difference between Kelvin and Celsius, of course, is that Kelvin has an absolute 0 definition. So 0 Kelvin is just, you can really say that 200 Kelvin is twice as much as 100 Kelvin. So it's, because actually it's basically expressing the movement of the molecules. And this is actually a scale which is absolute. Celsius isn't absolute. You cannot say like, and of course you can say that 40 degrees is twice as much as 20, but it's not true in the physical way. So in this case, we gain the geometric mean, which can also be calculated because you can calculate ratios. So the ratio scale is actually, you would say, the most advanced scale, where you can do most kind of relational statistical mathematics. Yeah. What is graphical data processing? A very important step in analyzing data is that you actually need to visualize data. And the reason why you need to visualize data is not only because you want to make insights plausible to others, but there may also be hidden insights which only will be present to you if you create a visualization. And this is the idea of graphical data processing. In its basic form, it's just a capture and presentation of visual information. like this. This was a current diagram. But in scientific computing, it aims for the interactive visual exploration of scientific data. And this is the key difference here is that it's not to illustrate knowledge, which would be like explanative communication, but it's about the exploration. So it's about the extraction of knowledge, which is called explorative communication. So the idea is that you don't want, the first one would be you know something and you want to make it plausible to others by visualizing it, which is often the case like in papers, for example, that you have some insights and you want others to understand them. And this can also often be done better by visualizing an aspect. But here it is about the actual gaining of new knowledge. So something which is not there yet, but you want to find out new knowledge. And this can also be divided into the internal and the external domain. So the internal domain would be the exploration of data, the derivation and the validation of hypotheses. So of course first we have some idea what the visualization might mean and formulate a hypothesis. And then in the public domain or external domain, you can discuss it with other scientists. So this is basically what is shown in this diagram. We have this private and this public realm. And we start with exploration. So we investigate data by visualizing data. Then we gain new insights. And then we have evaluation. So we formulate hypotheses and validate them. And then the synthesis is actually comparing it to other insights from other scientists, and a presentation would be like, for example, a conference. So this is basic idea, and of course you might ask, what is all the fuss about? So why do we need visual exploration? And I mean, sometimes also in papers we wonder if all visualizations would be necessary. But there's actually a famous example for data, which tells us a lot about why visual exploration is really crucial in understanding data. So this is the so-called L-SCUMP quartet in 1973, time to go. And basically you see it's just a very small, really simple, very small data set. And we have some data. We always have an x and a y. So the y is the x. So basically it's got four functions which are shown here. And of course we can apply some basic statistical functions to this data in order to understand it better. So this is what can be shown here. So if you analyze this by means of statistical methods, then you would get, for example, we have an arithmetic mean, which is 9, we have a variance, which is 11, we have an arithmetic mean of the y's, which is 7.5, we have a variance, which is 4, and there's also a correlation, which is, there is a correlation, so it's a random, not the mid-size correlation, so 0.816. And we can also fit a linear regression in the data, like this. And we also see, okay, x1, x3, and x3 are the same, right? It's obvious. We see that x4 is nearly constant, there's just a single outlier. And we see that the distributions appear to be fairly homogeneous. It's a very heterogeneous distribution. So let's say, okay, that's it. So kind of boring. But if you actually visualize this data, you will immediately see what is hidden in the data. So if you immediately see, okay, if you look at this, you would immediately be able to say how it would probably continue, right? So it's just like a parable. So maybe you throw a ball or something. And also the same goes for this one. You can immediately see, okay, still a straight line except for this one outlier. Also this one. And here, you can also see what how you would probably be able to continue the points and further axis. So as you can see here, it's I mean, it might seem a little bit trivial, but it's actually, it was, at the time it was published, it was very surprising, and also it was a little bit disappointing for many people, because the interesting thing here is that this is really a very, very small data set. And you can probably even memorize each data, so it's really, really small. So it's not big data, right? It's very tiny data. So it's just a couple of values. And still, you have just a couple of values, you could easily count them one by one and memorize them. But still, you don't immediately see how they are correlated, right? So without the visualization of this very tiny data set, you wouldn't have a clue what the structure of the data is. So this is really crucial to visualize the data to actually understand what the structure of the data is. And the reason why this was disappointing is that, I mean, imagine if we have really, big data. So we don't have like 20, 30 items of data, but 30 million or 30 billion, 30 trillion, yeah. So really big data, so terabytes of data. So imagine how hard it could be to actually find this kind of hidden knowledge in the data if we had so much data. So we couldn't easily visualize it, right? So even in a very small data set, there can be hidden information which needs visualization to actually understand them. And of course, this holds much more for larger data sets very often. So what we can take away with this example is that the very first thing we should do with unknown data is, of course, visualizing them. It also helps you to see, okay, there is an outlier, so this certainly doesn't belong here. And also to get an understanding of the scale of the data, of the value range, if they are plausible or not. I mean, of course, it depends on what the units of the axis actually are. Right? It's some kind of sensor measurement, and you need to understand how the sensor works. That's also something which is often not understood thoroughly, because often there is the problem with the companies is that they hire some people as data scientists, and then they do all this kind of investigation, and they have all these nice algorithms, and of course they know how to cluster the data and how to apply statistical analysis on the data, and also to do how to apply machine learning algorithms and neural networks and stuff like this, and random forests and you name it. But the problem is that these people often don't have a thorough understanding of where the data originate. And for example, if it's a sensor reading, you first have to understand how the sensor works in a physical way. If you don't, then you cannot really understand if the data are plausible or not. And so the very first step in understanding data is always thinking about where the data come from, and then visualizing it. And then you can apply the nice algorithms after all these other steps like preparation and so on. But be very careful that don't trust your data. Because it can be actually dangerous to do that. For example, I once had the example that I had a data set, and the data set was sensory reading of a windscreen of a car. And there was a sensor which measures the amount of rain coming from the windscreen. So the idea was we could use this data from a large fleet of vehicles as a prediction for rain cells. Right? So we can actually detect if there's incoming rain, because vehicles would report that they have incoming rain on the windscreen because of this nice sensor which measures, actually it's a photocell which measures the decoupling of light, which is happening by the water on the windscreen. So the more light is eliminated on the way from one sensor to the other, the more heavy the rain is. So that was the